Hello viewers, so I have this question that says, assuming that the mass of the largest stone that can be moved by a flowing river depends upon the velocity of water, the density of water, and acceleration due to gravity g, show that m varies at the sixth power of the velocity v. Alright, so this question is under dimension analysis. So to solve this question, the first step we're going to take is we're going to show the dependence of mass on velocity, density, and acceleration due to gravity. So we're told to say mass depends on velocity, density, and acceleration due to gravity. Now, what we have on the right side here, the v for velocity, the rho for density, and g for acceleration due to gravity, are having certain powers that we haven't established at the moment. So we're going to represent those powers that are supposed to be given to V, rho, and G with letters. We can pick any letters. I'll pick A, B, and C. So I'm going to give V to the power of A. I'm going to give rho the power of B and G the power of C. So that's the first step. The next step is to replace the proportionality here with an equal sign and the proportionality constant. So that's what we are going to do. We'll say our mass is equal to K multiplied by V, that is multiplying by rho, that is multiplying by G. The powers are still there. This is to the power of A, the power of B, and to the power of C on the other side. Now that we have replaced this, we can now start doing our working. So we are going to look for the units of both what we have on the left side and what we have on the right side. On the left side, we have mass. Mass is measured in kgs, so we are putting kgs. Then on the right side, forget about the k. K is a constant, so it's not considered under dimension analysis. So our main concern is v, rho, and g. So for v, this is velocity and is measured in meters per second. M multiplied by s to minus 1. So that's what we have. And this whole thing here is given to the power of a. So we have that power of a. Then this is multiplied by density is measured in kgs per cubic meter. So kgs per cubic meter, like that. And this whole thing is given to the power of b. Then this will multiply by acceleration due to gravity. Acceleration due to gravity is still acceleration, so it's measured in meters per square second. And this also is given to the power of c, like that. So that's how we do it for the next step. Now, after this, since we have introduced our units, we are going now to introduce our dimensions. On the left side here, we have kg. Kg has a dimension of m because that's mass. So kg is a unit of mass and has a dimension of m. Then what we have here is meters per second. So meters is a unit of length and seconds is time. So what we have there is LT to minus 1 and still given to the power of A. The next one we have here will be kg is still mass, so it will be M. Then L to minus 3, and this must be given to the power of B. Then the next one is we have L T to minus 2. And this whole thing here as well must be given to its power, which is C. So that's what we have there. Now, to simplify what we have on the right side here, we're going to multiply what we have in brackets there with their powers so that we simplify it. On the right side, let's start with the left. The left is to have M like that. On the right side, what we have on the first part is we'll have L now given to the power of A. Remember, all those inside there are given to the power of A. So this one here is given to the power of A. Even T is given to the power of a. When a power is given to a power, those powers are going to multiply. So we multiply this power and that power to get the power for this t here. So when we do that, you see that we're going to get a minus a. So t is given to the power of minus a. And then in the second one, m will be given to the power of b, and L will be given to the power of minus 3b. Remember again, the power is multiplying by the power. And in the last part, our L will be given to the power of c, and our t will be given to the power of minus 2c. So that's what we have on the right side now. All right. Now to simplify it, everything that is the same, for example, we have L here, we have L here, we have L here. Like terms together are going to multiply and the powers are going to be given. For example, if we have x to the power of 2 multiplied by x to the power of 3, our answer here will just be x. We add our powers, meaning x2 added to 3, and our answer will be x to the power of 5. So this same concept is what we are going to use there. When like terms, the same bases are multiplying, their powers will just add. So let's do that. So on the left hand side, we still have our m like that. Then on the right hand side, L in the first box, this L here is going to multiply by that L and multiply by this L. So what we'll have for L is, we'll have L given to the power of A, since we say the powers are going to add. So A added to minus 3b, but then since we have a minus, when we say plus minus 3b here, what we have here is this plus is going to be cancelled by the minus, so we're going to have minus 3b there, and this will be added to c on the other side. So that's what we'll have for that part. And then for the next part, let's pick t. So t will be given to the power of minus a added to minus 2c. So when we say added to minus 2c, that will still give us a minus 2c. So we'll just have minus a minus 2c for that. And then the last one is m. M is given to the power of, it's just alone, so it's just given to the power of b. So this is what we have now as our dimensions on the right side. All right. So that's what we have. Now, when you reach this stage, we're going to be comparing what we have here with what we have on the left-hand side. Now, what we have on the left-hand side can be rewritten in this format. We can write it in this format to say, we have m, then we have l to the power of 0, then we have t also to the power of 0. So the dimensions we have on the left side is m, l to the power of 0, then t to the power of 0. Anything to the power of 0 is 1. So t and l are to the power of 0. So when we multiply them, they're just like a 1. And still, we are going to have only m here. So we are bringing this in order to understand as we equate what we have on the left side to the right part. So now let's do the equating. What we are going to do is, you see this L here, we are going to compare it with the L we have on the left hand side. So let's put that here. We have L given to A minus 3B plus C, so that we understand again, minus A minus 2C as a power for that, and M to the power of B. So let's now compare. Let's start with the M. The M on the other side here, is having a power of b, and on the left hand side here is having a power of 1. So what we are going to do is we are saying the power of b is equal to 1 on the other side. Since the power of m that we have here is 1, it means the power of m that we have here is equal to the power of m that we have on the other side. So let's write that, meaning our b is equal to 1. So we are done with that one. We go to the next one. Let's go to t. T is having a power of minus a minus 2c here, and on the other side t is having a power of 0. So we're equating the powers. So what we have there is a minus a minus 2c. This will be equated to 0. And then for the last part that we have is we have L. L here is having a power of a minus 3b plus c, and L on the other side here is having a power of 0. So what we have there is just a minus 3b plus c is equal to 0. So yeah, hope you understand how we are equating the powers. T is to the power of minus a minus 2 on the right side, and on the left side t is to the power of 0. So the powers we have here are equal to the power we have on the left hand side, which is 0. Then for L, we also have this power here, a minus 3b plus c, and on the left hand side we only have a 0, so it's equated to 0. And M here we have a power of b, and on the left hand side we have a power of 1. We don't need to show 1 if that's the power we have. So it's a power of 1 we have there, and this is what we have basically shown here. So the job that we have here is to find the values of a, b, and c. All right, so that's the job we have. So to find the power of a and b and c, or a, b, and c, we need to solve these equations as simultaneous equations, or we solve them simultaneously in other words. So we have b to be equal to 1. B is already found. We understand that the power that we have for b is 1, or b as a power is equal to 1. We need to establish what a as a power is equal to and what c as a power is equal to. How do we do that? So let's start with a. So from the second equation, this one here, minus a minus 2c is equal to 0, making a the subject. We'll find out that our a, let's put it there, our a will be equal to minus 2c. It's called minus 2c because we're going to take this a, since we want it to be a positive, we're going to take it on the right hand side, and it will be positive there, meaning our a will be equal to minus 2c. So that's what we've established there. A is equal to minus 2c. After doing that, we can now bring that into another equation so that we find a certain value. So let's bring it in the third equation, this equation here. A minus 3b plus c is equal to 0. So where there is a, we're going to replace with minus 2c. So we'll have minus 2c minus 3. Now b is 1, so that's 3 multiplied by 1. Then added to c is equal to 0. Like terms together, we'll have minus 2c plus c, then minus 3 is equal to 0. Then what we have here is minus 2c plus c. This is going to give us minus c, then minus 3 is equal to 0. All right. So what we have there is, we now have to say minus c minus 3 is equal to 0. Again, we're going to take our c on the right hand side where there is 0 so that it becomes a positive, and when we do that, we're going to find that our c is equal to minus 3. So it implies to say we have found the value of c. Now we have the value of c and we have the value of b. What is remaining is just establishing the value of a. All right. So since we have the value of c and b, let's put those values in this second equation here that says minus a minus 2c is equal to 0. All right. So replacing with that, we'll say, or rather, we can basically just use this one here. You see this one, we established here to say a is equal to minus 2c. So if a is equal to minus 2c, we can just bring the value of c here and we'll be able to find our answer. So let's do that. We'll say a is equal to minus 2c, and this is equal to minus 2 multiplied by c is minus 3, so minus 3 there. And this will be equal to negative negative will give us a positive. 2 by 3 is equal to 6. So it means the value of a is 6. So we now have the value of a to be 6. We have the value of c to be minus 3. And we have the value of b to be 1. So yeah, our job is done. All we have to do is now take it back to where we started from. So on this side here, you can see the relationship we're looking for is the relationship here. So we have found now the powers of A, B, and C. All we have to do is bring it back here and replace. So let's do that. All right, so what we have now is our M is equal to, we can still leave the K, V to the power of A. The power of A is 6, so we put 6, and density is given to the power of B, which is 1. We don't need to show that. And G, which is given to the power of C, which is minus 3. So this is what we have here. M is equal to K, V to the power of 6, then rho to the power of 1, G to the power of minus 3. This can be written like this as a formula. M is equal to V to the power of 6, then multiplied by density divided by acceleration due to gravity to the power of 3. So this is the formula that we have here. Now, this is proving to say, from the question they are saying, we need to prove that m varies at the 6th power of the velocity v. We can see the power that we have for velocity is 6, and it proves to say m varies to the 6th power of what? Velocity v. So it has been proven. We can conclude to say m is proportional to v, directly proportional to v to the power of 6, hence proved. Yes, so we have proved that.